Hi guys, and welcome to Learn Extra Live Physical Science, because it's a Tuesday. As you can see, Bruce is joining me today, and it is grade 11s. Finally, they have been waiting for this session. I know during the grade 10 show they were saying, "Oh, I can't wait for the grade 11 session."
Okay, well, that excited, eh?
No, seriously, that excited, and I'm not lying, and you know who you are. Today we're going over
electromagnetism.
It's a big word for me to say, electromagnetism, and I think it's going to be lots of fun. Hey, Bruce?
Well, we hope so.
Yeah.
Let's see how we go, huh?
Yeah,
Great.
definitely. Yeah.
Good.
So, Bruce, take your...
I'll get to my seat.
Yeah,
Yep.
your seat. Take your place. Guys, I just wanted to give a big shout out to Liberty, and thank you so much, guys, for making this all possible. You guys are awesome, and we dig you lots and lots and lots. Also, don't forget to chat to us on Facebook. It's facebook.com/Learn Extra, and that's with an XTRA. Also chat to us on Twitter @Learn Extra. You can pop us any questions. There's no question too silly, only the one that's asked after the exam. And guys, don't forget, we're giving away a Casio calculator, and that's to the best post, whether it be about inspiration, you want to say hello to us, if you help out a fellow mind setter, you can even post quotes on our page. We don't mind. Just get chatting to us and get learning more and learning extra. And I think without further ado, we're going to get straight to Bruce's section, or to his lesson. And please don't forget to ask all of your questions onto the page, and we will be going through in the last 50 minutes of the show. Okay, Bruce, now is your time to talk. Take it over.
All right, Indy, thanks very much. And guys, welcome to today's show. What we're going to be doing today is having a lesson on electromagnetism. Okay, now I'm not too sure how many of you guys in grade 11 have actually already covered this in your lessons at school. Some of you may have, and then it's going to be it's going to be a revision lesson, and as we get close to exams, hopefully as a revision lesson, this will help you guys with those questions that do pop up in your question papers. But those of you guys who haven't done it, then just follow what I'm going to do, and hopefully when you guys do get to do it, this should be fairly familiar to you, and hopefully give you sort of an edge on the rest of the people in your class. But guys, if we have a look at the heading electromagnetism, just the word or just the title of the lesson itself should start conjuring up all sorts of ideas in your mind as to what we could possibly be talking about when we say electromagnetism. So let's break it up to electromagnetism. And I'm sure a lot of you guys are saying, well, probably something to do with electricity, electrons, movement of charge, something like that. Magnetism to do with magnetic effects, magnets and things like that. Magnetic fields, which you might remember from grade 10. Well, guys, that's exactly what we're going to be having a look at. And we're going to be taking some concepts from grade 10 and expanding on those concepts, making them a little bit more, hopefully a little bit more sort of valuable to you, plus introduce some new concepts and introduce one or two new laws. So, guys, what are we going to have a look at? Well, first of all, if we look at this, we've got a basic description or explanation of what electromagnetism is. And electromagnetism describes the interaction between charges, currents, and electric and magnetic fields to which they give rise. So in other words, what they're trying to say here, I'll just get my pen loaded up here. What they're trying to say here is that we're going to have charge and electric current. So charge, remember electric current, the flow of charge, and we're going to have a look at electric and magnetic fields to which they give a rise. So what we're trying to say here is that there's an interaction between electric current and magnetic fields, and with magnetic fields and electric currents. And that's how we're going to approach today's lesson. It's by having a look at how electric currents can generate a magnetic field, and then, or should I rather say, produce a magnetic field, and how a magnetic field can produce an electric current. Guys, it's quite topical. Also very important for grade 12 as well. So you guys who are busy preparing for your exams and who are going to be writing on this, remember guys, you're going to see it again in grade 12. And if there are grade 12 learners watching the show, hopefully this will also be able to help you. Right, so let's just run through and see what we've got here. Guys, a very important statement, and I'm going to mark it over here. An electric current creates a magnetic field, and a changing magnetic field will create a flow of charge. That is an electric current. Exactly what I just tried to tell you guys a little bit earlier, that we've got this interaction between electric currents and magnetic fields. Okay. Now, we're going to kick off by having a look at magnetic fields associated with electric currents. Now, hopefully you guys have done this little experiment, but what happens if I take a conductor, okay, and I've just tried to draw it over here, and I'm sorry, I don't want to cut this top off just yet, but the important thing is that if I take a conductor and I pass an electric current through that conductor, and I bring a compass close to that conductor, we're going to see that the compass needle is going to deflect. Now, what causes a compass needle to deflect? Well, I'm sure you're all going to be jumping up and down saying, well, it must be a magnetic field, because we use compasses on the Earth to look at direction and stuff. We know that the Earth has got a magnetic field, and that's absolutely correct. We will only get a deflection or movement of a compass needle if we've got a magnetic field. So, if this compass over here, okay, is going to deflect, then what we must have is a magnetic field that surrounds that current carrying conductor. And what I've tried to indicate here is a little arrow, which gives me my direction, okay? So the direction of my electric field, which is going to be going up the conductor itself. Now, the important thing is what does this magnetic field look like? Well, the magnetic field is very simply described as a circular type of field, which is presented around a current carrying conductor. So when we draw it, we generally draw it in this sort of fashion to try and represent a three-dimensional pattern on a two-dimensional surface with these concentric circles, or should we rather say the symmetry of circles, the pattern getting ever bigger and bigger as we get further and further away from the actual conductor itself. You'll find that the magnetic field lines that are created are very close together when they're close to the conductor, and as we move away, those field lines get a little bit more spread out. So if I had to draw another one like that, you'll probably find it'll be quite spread out, where you can see, guys, that over here, and let's just put it in there, we've got very, very close lines in those positions. Okay, so, guys, what do we got? We've got this magnetic field pattern, okay? But the important thing now is, with a magnetic field pattern, we have to now be able to give that magnetic field a direction. You'll remember from grade 10 when we just spoke about magnets, and we had a north pole and a south pole. You were able to describe magnetic field lines that originated from a north pole and terminated or finished up at a south pole. There was a direction to them. So we have to do exactly the same thing here, but the question is, how do we do or give circular magnetic field lines some form of direction? Well, we have to introduce this rule over here, which is called the right-hand thumb rule. Okay, and the right-hand thumb rule is actually very, very simple to apply. If you take your right hand, and if you guys can do this with me at home, and we put our finger out in a sort of hitchhiking position, or should I say our thumbs out in a hitchhiking position, okay? And basically we take the thumb and we point that thumb in the direction of the electric current. The natural curl of the fingers, so if I can put it like that, the natural curl of the fingers will represent the direction of the magnetic field lines. So, if I went up here, and I went back to my original diagram, and I said, right, my current's moving upwards, so therefore my thumb must be pointed upwards. Which way are my fingers pointing? My fingers are coming sort of out of the board and doing that and going into the board. So how would we represent it on the diagram? Well, we'd represent it like that. And you see what I'm doing now? I'm just putting my little arrows in that particular direction. So you can see now that we are moving this way around. The curl of the fingers, the magnetic field lines are moving this way around. And that's what we call, whoopsie, that jumped a bit. Okay, let's go back down. There we go. Right, can you see now, this is what we call an anti-clockwise direction. Okay, it's an anti-clockwise direction. Now, whether we have got the magnetic field patterns moving in an anti-clockwise direction or a clockwise direction is going to simply depend on the direction of curl of those fingers. The graphic that I've got over here is also just trying to show you a little bit in a different way that if we've got, for example, if it's at an angle, we just simply put our thumb in the direction of the angle of the conductor, my curl of my fingers, or if it's straight up, like I've got over here, can you see now how my fingers are curling? And you can see that they have now put very nicely on the diagram the arrows pointing in the direction of that magnetic field. So guys, quite a simple, quite an easy way of being able to determine our magnetic field lines. Okay, right. So if we just run through quickly the description, this is a simple method of finding the relationship between the direction of the current flowing in a conductor and the direction of the magnetic field around the same conductor. This method is called the right-hand thumb rule. Simply stated, the right-hand rule says that the magnetic field lines produced by a current-carrying wire or conductor will be orientated in the same direction as the curled fingers of a person's right hand in the hitchhiking position, with the thumb pointing in the direction of current flow. Okay. Right. Well, guys, that should be nice and simple now. However, we may be faced with a situation where the orientation of the conductor might actually be different. We spoke about our conductor and we saw that the conductor was now in a sort of vertical position. But what happens now if I start to have a look at the conductor from the top, a vertical view? Well, we can represent the vertical view by having a look at the way that I've represented the conductor in these particular diagrams. What's actually happened is that we've sort of taken a cross section, we've sliced through the actual conductor, and we're now looking down on top of the conductor. The question is, when we look down at the top of the conductor, do we know in which direction the electric current is flowing? Well, that's where we get these little symbols, and you'll see now that inside the actual conductor, I've placed little symbols there for you. One has got a little X, okay, or a little cross. The other one is more of a little circle, a little dot, okay? Now, those very simple little symbols are telling us the direction of my electric current. When we have the cross placed in the circle, what we are having is electric current moving away. It's moving away from you. Okay, in other words, in this case, it's moving straight into the board. If you guys can see what I'm doing here, it's moving straight into the board. If I've got the conductor like that, and I've put a little dot in it, what it means is the electric current is coming towards me. Okay, it's coming towards me. Now, what's an easy way of trying to remember this? Well, I always tell my students at my school that the easiest way is to remember playing a game of darts. So when you stand there with the dart and you're going to throw a dart into a dartboard, okay, what happens when you throw the dart and you throw the dart away from you? What do you see? You normally see the cross feathers of the dart actually moving away from you. So therefore, that's going to represent the cross feathers of the dart. And what happens if your mate gets cross with you and he throws the dart back at you? What are you going to see? Well, you're going to see the dart point coming straight at you, not so. So that little dot there can represent the dart point coming towards you. Okay. Now, how does this work with my right-hand thumb rule? Very simply. Right, let's take the guy moving towards me. My thumb must now move, or must point, shall I rather say, in the direction of the current. So it's coming towards me. It's coming out of the plane of the board. So there it is. Where's my fingers curling, guys? Can you see how my fingers are curling? In that direction. So if I have to now draw this, I can simply draw, and as neatly as I can draw the circular magnetic field pattern with the direction moving like that. Can you see that? That's the curl of my fingers. Again, we've got another anti-clockwise. We've got an anti-clockwise pattern. Okay. Now, what about the guy going inside me? Well, if I turn around like this, and it's going away from me now, okay, so my thumb must now point inside the board, or into the board. Where's the curl of my fingers now? My fingers are curling again. We've still got the same pattern, like that. But the curl of my fingers are now in that direction, so the field lines, the magnetic field is going to look like that. And therefore we have a clockwise pattern. And there, guys, is very simply how we can actually predict the magnetic field pattern around a current carrying conductor using my right hand thumb rule. Nice and simple. Okay, quick summary of that. Let's have a look. Use your right hand, use the right hand thumb rule to determine the direction of current flow. Curl the fingers in the direction of the field. And lastly, place arrows on the field lines to show magnetic field direction. Sorry about the spelling there. That should be field, not filed. But there we go. Step 1, step 2, and step 3. Hopefully nice and simple. So quickly, let's have a look at this little exercise that I've got here. So if you can practice this at home, let's see if you can do it. It says indicate the direction of the magnetic field lines around the following conductors. Okay, I just need to put in some directions for you. So we're going to have current flowing in that direction there, and in that current, conductor is going to be flowing downwards. So here we go. If this guy now is if the current's moving upwards, can you see now where my curl of my fingers are? My thumb's pointing up at the angle in the direction of the current. My fingers are coming this way, so I'm going to draw my field pattern like that. Whoopsie. Okay, I think let me just go and redo that. Make it a bit neater. Like that. You can see now. And where's the curl of the fingers? The curl of the fingers is in that direction. Okay, that should be coming around as well. Okay, and my field patterns like that. This guy, remember what we said? We're looking at a cross-sectional view. The current is flowing away from me, so what happens is that my thumb must now point inside or into the conductor. My fingers are curling this way, so I'm now going to draw my field like that. Okay, remember curling, it's basically curling this way, so it's coming around in this direction and going in that direction. So you've got a nice clockwise pattern here. And this one, guys, well, the direction's downwards, the thumb is pointing downwards, the curl is going this way. So what's happening now, so if I draw it like this, can you see now, where's the curl coming? There it is, it's coming around, out the board in this way. Therefore, we're going to have my magnetic field looking like that. Okay. All right, guys. Indy, I think, are we ready for a break? Have we got some questions at this stage?
We do have a few questions, but what I think we'll do is we're going to take a quick break, and then I'll go through all of the questions with Bruce. Now's your time to actually get posting those questions. So if there is anything that you're not understanding, I'll be going over it during the break with Bruce. Don't leave. Go get yourself a glass of water, Sami, jump up and down to get the blood going. We'll see you now to learn more and to learn extra. Welcome back, grade 11 Mindsetters. This is physical science and it's a Tuesday, so I hope that you're all learning more and you're all learning extra. You're tuning in and the page is quite quiet with questions. You're all saying like how you've either written your exams or you are writing your exams or you're loving the show, which is awesome. So I'm taking that there's no questions as that you're all understanding, which is even better. Guys, I think let's get straight to the lesson. Don't forget we are going over questions in the last 15 minutes of the show. You can post them your questions on facebook.com/learn extra, Also chat to us on Twitter at LearnExtra. And I think without further ado, he's going to get straight back to Bruce. Bruce, take it away.
Right, thanks, Indy. Thanks very much, guys. Hopefully everyone's quite happy with what I've spoken about at the moment. We're just into some fairly simple stuff in terms of getting directions of magnetic field lines. And just before we had the break, I went through this quick question, and we were able to show the direction of the magnetic field lines based on those particular conductors and the direction of the current flow. But here's now another question which we can ask you guys, and that is now to take it and reverse the situation. So in other words, instead of me giving you the direction of the current, can you tell me now the direction of the current if I gave you the magnetic field and I gave you the direction of those magnetic field lines? Are we able to do them? Well, guys, all we have to do is still keep working with the right-hand thumb rule. Okay. Instead now of pointing my thumb in the direction of the current, I must now take my fingers and point the fingers, or the curl of my fingers, in the direction of the magnetic field lines that are in the question. So if we look at this one over here, can you see now that these magnetic field lines appear to be coming from this direction and moving around, okay, in a sort of anti-clockwise direction? So what is going to be, how do I curl my fingers? Well, it's simple. If it's coming anti-clockwise, I must curl my fingers anti-clockwise, like that. And where's my thumb pointing, guys? My thumb is pointing straight up the conductor. So there's my direction of current, and if I wanted to do it, boom, I put a nice arrow onto the conductor, and there's my direction of current. What about this one over here, guys, where we've now got a situation where we've got sort of that cross section, and we can see now that I've got a clockwise direction of my magnetic field lines. So what I have to do is take my finger, okay, and what I'm going to do now is take them and curl them in the clockwise direction, which is going to be like that. So in other words, they're coming around in a clockwise direction. There we go. Where's my thumb pointing, guys? It's pointing directly into the board, isn't it? How do we represent that? Going away from me, directly into the board, we simply put a cross, and there's my answer. Okay. So guys, you can see now that the right-hand thumb rule is actually quite a versatile, quite a flexible little tool to have when it comes down to current and magnetic field lines. But now, guys, we're going to change things slightly. We've seen now how electric current can produce a magnetic field. Right in the beginning of the show, I spoke to you guys and said, but hang on, there's also the ability of a magnetic field producing an electric current. Let's see how this all works. And this is going to be the second part of today's lesson, where we're going to be looking at current induced by a changing magnetic field. Okay. And this was done by a scientist by the name, or should I say first discovered, by a scientist by the name of Michael Faraday. Now, this goes back a long time ago. So this is not new science. It was stuff that the guys sort of got hold of and understood in the sort of early to mid 1800s. And what Michael Faraday discovered was that a voltage could be generated across a length of wire whilst moving a magnet nearby. So in other words, what happens is that if we had a conductor, okay, and we had a magnet that was nearby, and that conductor was connected in some form of circuit, it was found that when that magnet was brought into close proximity to that conductor, there actually was an electric current flowing, and that electric current flowing created a voltage, okay, or what we sometimes call an EMF, an electromotive force. Now that's quite interesting, because what it means now is that the wire was exposed to the magnetic field lines. Here we go, underlining it for you. The wire was exposed to the magnetic field lines, which he concluded must have induced, and there's a very important word, I'm just going to put that into a little bit of a box there, which induced the potential difference and hence the current flowing through the conductor. Guys, the word induced means that it has been caused by. So we're saying that the magnetic field lines is causing an electric current in that conductor, and hence a potential difference or voltage to be created across that conductor. Okay, and that's where we now come up with Michael Faraday's phenomenon, which he called the electromagnetic induction. We've created an electric current through a magnetic field, and this current has been induced. Electromagnetic induction. And what I've got over here is a definition or an explanation for you, is that the magnitude of the EMF induced, in other words, the size of that EMF induced in the conductor, is directly proportional to the rate of change of magnetic flux. The rate of change of magnetic flux. Now, here now is this word, is a new word called flux. All we mean by, when we talk about magnetic flux, we're talking about the magnetic field lines. Okay. So therefore, what's important about when we talk about the rate of change of magnetic field lines or magnetic flux is that how quickly or how many field lines are actually going to be interacting with the electric coil. Okay, with the electric conductor. That conductor is then going to be induced and the current will flow, and we can change. In other words, we can make the current bigger or smaller by actually looking at this thing called rate of change of magnetic flux. And guys, this is something that now we're getting a little bit more complicated, a little bit more conceptually difficult. So just sort of hang in there and just keep thinking about what I'm trying to say here. Now, what are we going to do? Well, as I've said here, this means that the size of the induced EMF or current is determined by the strength of the magnetic field. How strong is that magnetic field? Okay. And secondly, how quickly will the change of magnetic flux occur? In other words, do we have a strong magnet or weak magnet that's going to be interacting with the conductor? And the other thing is how quickly are we moving that magnet close or away from that actual conductor. Now, what I'm going to show you guys is a little simulation. And I want you to have a look at this simulation. I'm going to be doing it, get the simulation up. But I want you guys, if you can, to have a look at that website address, because you guys can go online yourselves and you can go and actually get this simulation from this excuse me, from the site called FET Simulations, and FET is spelled P-H-E-T, okay? And if we get this website address into your computer, you'll be able to actually go and get the simulation itself. Now, before we go and do the simulation, how does it actually work? Well, what we're going to be doing now is having a look at what we call induced EMF or induced electric current. Okay, and we're going to introduce a rather fancy looking piece of equipment which is called a solenoid. Okay, now a solenoid is simply a circular loop or circular loops of conducting wire which are used to generate the EMF in the conducting wires themselves. So it's just an arrangement of conducting wires in this loop, okay, and we call that a solenoid. Okay, now over here is my magnet. And what I can do with the magnets, I can take the magnet and I can move the magnet in and out of the solenoid. Remember, guys, that the magnetic field lines of the magnet will then be cutting or moving into the coils, cutting the coils. Whether we pull it in, it'll be going in one direction, and when we pull out, it's going to be in the other direction. This is the basics of electromagnetic induction. So let's have a look at the simulation, and let's see if we can get this thing to work. Okay, so what I've got over here, I just need to try and make it full screen. It doesn't seem to want to. There we go. Hang on.
Not the one next to it.
This one.
Yeah, but she
doesn't seem to be working.
Maybe the selector?
No. Doesn't seem to be working, unfortunately.
Well, you know what, Bruce, you give that a bit of a fiddle, and while you're doing that,
okay.
I'll chat to the mindsetters, because you know I love talking, right? Guys, don't forget you can ask us questions on Facebook. That's facebook.com/LearnExtra. Also on Twitter @LearnExtra. We've also got this awesome calculator to give away. On Mondays and Tuesdays, we give away to the grade 10s, 11s, and 12s. So, guys, you have a pretty big chance of getting one of your very own scientific calculators. Bruce has managed to get it full screen. I think maybe sometimes it's just the pressure. It happens to me. I can't do anything if I've got thousands and thousands of mindsetters watching me on TV. I think back to you, Bruce.
Okay, thanks, Cindy. Well, that was a little bit of a technological challenge that I was faced with
And
over
you
there.
overcame it.
And I overcame it. Thank you very much. No, there was something there that was blocking the actual minimize, maximize, but we managed to figure it out.
Fantastic.
So, guys, there we've now got the full screen now of the simulation. Now, if you have a look over here, I've got basically a coil, one single loop of a solenoid coil. Okay, over here I've got a magnet, okay, with its north pole and its south pole, and what I've got attached to this is a meter. Now this meter is going to measure voltage. Okay, now the important thing is to watch what happens to the meter when I actually move the magnet into the loop. Okay, so I'm going to pick this up. Well, it was going to work. And, sorry, let's try and, there we go. We move it in, and we move it out. Let's move it in, and we move it out. We move it in, and we move it out. Okay. Guys, did you see the deflection on the actual meter? Okay. When that deflection happens, did you notice now the direction of the deflection depending on the direction of the actual magnet? So if I move the magnet in, notice it deflects to the left. When I move it out, it deflects to the right. Move it in, deflects to the left. Move it out, it deflects to the right. Okay. Why are we getting a deflection in two directions? Well, guys, that's because the magnetic field lines created by the magnet, okay, the magnetic field lines are moving in one direction, going into the loop, and moving in another direction, or should I say moving outwards as we remove the magnet from that loop. Now, let's now increase the number of loops. Okay, I'm going to put 2 loops in there. Okay, now I'm going to do exactly the same thing. And I want you to watch the deflection there and there, there and there. And hopefully you should be able to see that the extent of the deflection is actually a little bit larger when I've got 2 loops. Okay, let me put a 3rd loop in there. Okay, let's bring this down and line it up. Let's bring it in. Watch the deflection in and out. In and out. And you can see now that my deflection is getting even bigger. So what is that trying to tell me? Well, if this little meter is measuring voltage and the deflections are getting bigger, the voltage, the magnitude of the voltage is getting larger, okay, as the number of coils gets bigger and bigger. Therefore, the magnetic field lines from the magnet are able to cut more and more coils in the solenoid. The more coils the field lines can cut, the greater the electric current, the greater the voltage. So there, guys, is one of the big factors, very important factors, from Faraday's law of electromagnetic induction in terms of what makes the induced EMF bigger. It's going to be the number of coils in the solenoid. Now, let's have a look at this one. If I take my magnet and I move it in, I'm moving it in quite slowly. Have a look at the magnitude of the deflection. Okay. Now I'm going to try and move it in a lot quicker. Do you see now, when I move it in a lot quicker, can you see that that needle is deflecting a lot more? That deflection of the needle, deflecting a lot more, is also indicating a bigger or larger induced EMF. So what's the second thing we have to remember? Is how quickly are we changing the direction of the position of the magnet in and out of the solenoid? Remember what we spoke about in our explanation? It's the rate of change of magnetic flux. The rate of change of magnetic flux is going to be determined in terms of how quickly I move it in. So it's slowly, small deflection. Slowly, small deflection. very quickly, much bigger deflections. I've got a greater change of magnetic flux. And therefore, I'm going to have a greater EMF. And hopefully that is going to explain a little bit to you in terms of how we can create and how we can manage current that is generated in a conductor using a magnetic field. Okay. Indy, are there any questions up to this point?
There are. Let's have a look. How do you know? Let's hope that this is a good question. How do you know if a transformer is a step down or a step up transformer if you've got the primary and secondary coil?
Okay. Transformers after the break. We're talking about transformers after the break, guys. So hold that question. We'll be back with you soon on that one.
Okay. So that one will be after the break. Does magnetic field have the same meaning as electric field?
Does magnetic field?
Does magnetic field have the same meaning as electric field?
No, they don't have the same meaning, but you create a magnetic field from an electric field, okay? And you can create an electric field from a magnetic field. All right. So in other words, the two of them work in tandem. They actually, they sort of mutually work together. So if you have an electric field, which is generated by a current carrying conductor, you will create a magnetic field. And if you have a magnetic field, you can create an electric field, because then you'll be able to create, just like I've shown in that animation, you'll create an electric current, which will create its own electric field. Yeah.
Okay, one more question. I think then we're going to take a break. And this one is, what is Faraday's law concerning magnetic fields?
Well, basically, Faraday's law concerning magnetic fields, basically Faraday's law has got to do with electromagnetic induction. Okay, and electromagnetic induction is using a magnetic field to create an electrical current. So in other words, by moving that little magnet in and out of the coil, I've got over here, what's happening now is that we are moving it inwards, we're inducing the current in there. Okay, so therefore the magnetic field is creating the electric current. Okay. The magnitude, or how quickly I change that motion of the magnet, represents what we call the rate of change of magnetic flux, which is part of Faraday's law. Okay. The other important thing that we can also talk about here is that we can also increase the strength of the magnet. Okay. If I have a very strong magnet compared to a very weak magnet, a strong magnet will have a very strong magnetic flux, where a weak magnet has got a very weak magnetic flux. Okay, so Faraday's law also takes that into consideration. A stronger magnetic flux means you've got more field lines cutting the coils. You'll have a stronger induced current in the coils themselves. I think that's
I think that's a good one, and I think a few mindsetters were wondering that. So, but what I think we should do, Bruce, we should take a break.
Okay.
I know a whole bunch of you are asking for transformers, and Bruce has said that is coming up. So don't leave your seats. Stay tuned to learn more, learn extra. See you now. Hi guys, and welcome back to Learn Extra Live. This is grade 11, just in case you haven't been tuning in. Hope you had a big jump up during your break and you posted a few questions onto our wall and you're all having an awesome amount of time. Before I send you back to Bruce, I just wanted to let you know, please post questions now, because we will be going over it in the last 5 to 10 minutes of the show, and I think we've probably got about 5 to 10 minutes left. So guys, get posting. So without further ado, I'm going to hand you straight over to Bruce. Bruce, take it away.
Right, thanks Indy, and welcome to the last segment of tonight's show. A lot of questions have been coming in on the Facebook concerning transformers, and I have put a very short little segment together on transformers, just to make sure that we understand the basics of a transformer, how it works, and if we've got time, hopefully we can get a little calculation done just to show you how it works from a mathematical point of view. Well, the first thing we've got to have a look at, okay, in a transformer is, what is a transformer? Well, it's an electrical device that uses the principle of induction between the primary and the secondary coil to either step up or step down the voltage. Okay, and I'm going to basically put that down at that stage. We can also talk about it in terms of current as well, but let's just talk about it in terms of the voltage. So let's have a look now at a very simple setup of what a transformer is and explain a few of these terms. Well, guys, remember we're speaking about the principle of induction. Right, let's get my pen working again. The principle of induction, okay? Now, you remember, guys, in the previous lesson we had before the break, the principle of induction was using a magnetic field to create an electric field. Okay. Now, how does this all work? Well, a transformer is made up of two parts. One is called a primary coil part, or primary coil, and the other one's called a secondary coil. Okay, and the function of these coils is to either what we call step up or step down the voltage and or current. Okay, now when we talk about a step up transformer, that's a transformer that will take a certain potential difference, a certain EMF, a certain voltage, and make it bigger. Okay, a step down transformer will take a voltage or current, whatever, and it will make it smaller. Okay. Now, guys, where do we see, where do we see practical applications of transformers? Well, one of the easiest ones to think about are your cell phone chargers. Okay. Because your cell phone charger, or your cell phone charger rather, has got a little battery in the back there. And that little battery has to be recharged. Now, if you had to plug that battery straight into your main supply at home, I'm telling you guys right now that that battery is going to be a melted piece of plastic and chemicals and all sorts of stuff. It's going to be absolutely fried because those cell phone chargers really can only work at a maximum of around about 12 volts. However, we know that coming out of our main supply, we've got 240 volts that come out of our main supply. So therefore, how do we go from 240 volts down to 12 volts? Well, guys, we've got to step the voltage down. We've got to make it less. And therefore, inside your battery or your recharger, okay, that you plug into the wall, that you will have a little step-down transformer. Now, transformers don't have to be huge things. They can be very, very small. And if you look at some of the cell phone chargers these days, they're actually very small, compact little units. Okay, but they do the job, and that's the main thing. So, if we have a look at this particular setup over here, here now is what we call our primary coil. Okay, and we've labeled it over here primary coil. And can you see now that the primary coil is simply a set of conducting wires that are wrapped around one arm of this magnet. This over here, and let me just get my pen out again. In fact, that's colored. This over there is a magnet. Okay. All right. Now, that magnet, remember guys, we are now passing an electric current. There's my primary coil. So that's your input voltage. That's coming around and it's moving in a circular fashion. So remember, an electric current is going to create a magnetic field. Okay, that magnetic field is going to magnetize this iron. It's made of iron. Okay, so it becomes magnetized. So we call it the iron magnet. Okay, and it magnetizes this iron, and that magnetic effect now moves. Sorry, this thing has just moved slightly. Okay, this now moves. The magnetic field moves through the iron, and the magnetic field arrives at this coil over here. This is called the secondary coil. Okay, that is the secondary coil. Okay, now primary, secondary. Guys, what happens when magnetic field arrives at a conductor? And the magnetic field lines which are generated by the magnet cut the coils. We get an electric current, don't we? Okay, so what's going to happen now is that we are going to now cause or induce an electric current in these coils that are surrounding the right-hand arm of the actual transformer itself. But notice, guys, that the number of coils is very different. Here we've only got a few coils wrapped around the left-hand arm. Here on the right-hand arm, we have got a large number of coils. So therefore, can you see now that with a large number of coils, we are going to have a higher or larger amount of EMF? So can you guys tell me, is that a step up or step down? Well, hopefully you being able to tell me that this is a step up transformer. Okay. In other words, what we're doing is we're taking now the input voltage, okay? The input voltage now passes through the coils around the left-hand arm, creates a magnetic effect. It magnetizes this iron, okay? The magnetic field arrives here. Lots of coils. The magnetic field cuts the coils. Lots of coils means now we're going to have a higher voltage. And therefore, we've stepped up that voltage. And that's the basic principle. The opposite is true for a step down, where your primary input voltage, your primary coil will be much larger than your secondary coils. Okay. So, hopefully, let's have a look here. If we read through this. By choosing the number of coils in the secondary solenoid relative to the number of coils in the primary solenoid, we can choose how much bigger or smaller the induced secondary voltage or current is by comparison to the current in the primary solenoid. And so much, so by how much the voltage or current is stepped up or down. Guys, massively important. What is the basics of a transformer? The basics are, what's the size of our primary coil? What's the size of our secondary coil? What's the magnitude of my input voltage? I can then calculate the magnitude of my output voltage, which is my secondary voltage. Is it bigger? Then it's step up. Is it smaller? Then it's step down. That's the basics of it. Now, how do we actually apply this, or mathematically? Well, this ability to transform voltage and current levels according to a simple ratio determined by the ratio of input and output coil turns. Okay, it's the number of turns in the coil, number of turns in the solenoid, okay, versus the voltage that's going to be coming in. So what we've got now is a ratio. Here's a ratio, VP to NP, the primary voltage to the number of turns or coils of the primary solenoid. Remember, guys, where's my primary solenoid? We'll go back there. There it is. Can you see now those turns, those loops, creating that solenoid effect? Okay, so there we now have got that little relationship must be equal now to the secondary voltage, in other words, the output voltage, divided by the number of turns in the secondary solenoid. So P for primary, S for secondary. So it's the ratio of VP over NP to VS over NS. Okay. A lot of the times we can quickly rearrange this, and we can also write it like this. VP over VS is equal to NP over NS. And you might find those people who have done this section at school already, they might have been given this particular equation to have a look at. Okay, it's exactly the same thing. It's a ratio now of voltage, primary and secondary, to number of coils, a number of turns. Okay, and the current is exactly the same. Okay, the current can be determined by the expression VS IS. In other words, the voltage of the secondary multiplied by the current in the secondary is equal to the voltage in the primary multiplied by the current in the primary. And you will probably recognize where we got that expression from. It's from the power expression. P is equal to V times I. So therefore, what we've actually got is the power in the secondary must be equal to the power in the primary. And that's another very important little statement that we've got to remember, that the power ratio must be equal. The power generated in the secondary is exactly the same as the power generated in the primary. Now, I know we're running out of time, Indy. Is it time to go do a quick example on the board, or are there questions that are coming up?
Let's rather do a few questions.
Great,
I think probably that would be the best. And this one is actually from our 10,000th mindset to Marcel Cross, who's in the
Marcel,
studio.
good to hear from Marcel again.
Yeah. And what Marcel wants to know, and I hope this might be a quick one, it might have to be a verbal explanation. What does a transformer consist of? And he got this in his exam, and he had no idea. And what are the use of transformers?
Okay, let's have a quick look.
And Marcel actually got this question in his exam. Yeah,
okay, if we go back to my drawing quickly, what we've got is an iron block. Okay. Now, the reason why we use iron, to Marcel and to other viewers as well, the reason why we use iron is that iron is easily magnetized. The whole thing is working on being able to magnetize this. So you've got an iron block. You've got two arms of the iron block. We've got one arm, and I'm going to call this the left-hand side because I'm looking at it on my left. And around it, you've got these coils which are wrapped around, creating a solenoid. Okay? On the right-hand side, okay, we've got the right-hand arm. We've got another set of coils wrapped around it, also creating a solenoid. Okay? One of these is going to be the input, okay, which we call the primary, and there's the primary coil, okay? The other one is the output, which we call the secondary coil. So that is what a transformer is made up of. It's made up of an iron block, which can be easily magnetized, with conducting wires wrapped around each arm, creating a solenoid effect. Where do we use our transformers? Well, what did I say, Marcel? We use them in cell phone chargers to step down the voltage. Laptop chargers, we also step the voltage down, and things like that. Anything that we have to use smaller amounts of electricity, then we are able to step down the voltage. Therefore, we step down the current, and we can use it.
Fantastic. So, guys, I think we've run out of time. I know that there's lots of questions on the page. We will get somebody to try and answer them. If there is anything you are still stuck with, please email helpdesk@learnextra.co.za. We've only got a few minutes or seconds left. So I want to say thank you, Grade 11s, for an awesome show. Don't forget that winter school for Grade 11s will be starting from the 9th of July to the 12th of July. Keep checking our Facebook for more details to learn more and learn extra. Thank you very much and have an awesome day. Bye, guys.